Okay, good evening to all and welcome to the another session of the NPTEL course Heat Transfer. So this is our 10th session. So we'll be discussing about some practice questions related to the different topics. So let's have a brief recap of what are the contents that we discussed in the week 10 topic. Week 10. So there was a tutorial session. The first lecture was a tutorial session for the heat exchanger part. Then we moved on to the boiling part where we discussed about the pool boiling. And in pool boiling, we discussed about the pool boiling curve where we have the different regimes like free convection regime, nucleate boiling regime, film boiling regime, transition regime, etc. And also we discussed about some types of evaporators that are all used. Next, we moved on to the topic radiation, where fundamentals of radiations were covered. So, as we know, radiation is the third mode of heat transfer. We first studied, actually, this course was divided into like three major modes of heat transfer. First, we discussed about convection. Second mode is a convection, and third mode of heat transfer, which is radiation heat transfer. So actually, radiations are electromagnetic waves, which doesn't require any uh, medium or medium for its propagation. So we are basically studying about the thermal radiation part as it is. As I think you have noticed about the wavelength spectrum. So in the wavelength spectrum, so from zero point 0.1 micrometer to the 100 micrometer range covers the thermal radiation part. So we will be mainly discussing about this thermal radiation part. And in the thermal radiation part, discussed about what is a black body and also the different like absorptivity, reflectivity, and transmittivity of radiations, and also the emissive power, spectral emissivity, and types of uh, radiations, and also intensity of radiations were discussed and what is meant by a black body, its characteristics, etc. were discussed in the week 10 talk. So we will be doing some practice questions related to these topics. So let's get started with the first question. So this is from a heat exchanger part. So it's a steam in the condenser of a power plant is to be condensed at a temperature of 30 degrees Celsius with cooling water from a nearby lake which enters the tube at 14 degrees Celsius and leaves at 22 degrees Celsius. The surface area of the tube is given and the overall heat transfer coefficient is also given. So, so heat losses we can neglect. So we have to determine the heat transfer in the condenser. So as it's a phase change heat transfer is taking place. So it doesn't matter whether it is a parallel flow or a counter flow. So I will just draw the temperature distribution along the length of the heat exchanger. So steam is to be condensed. So steam is condensing at 30 degrees Celsius. So it's 30 degrees Celsius and temperature is entering, the cooling water temperature is entering at 14 degrees Celsius and it's 22 degrees Celsius. So the surface area is given as 45 meters square and the overall heat transfer coefficient is given as parts per meter square. So we need to find out what is Q, that is the heat transfer in the condenser. So Q, it's a simple like we already discussed. We already discussed similar type of questions in the previous classes. That is U0, that is overall heat transfer coefficient, A, LMTD. Okay, log mean temperature difference. So what is log mean temperature difference here? LMTD. That is delta Ti minus delta To divided by ln delta Ti by delta To. So what is delta Ti here? delta Ti is equal to 30 minus 14, which will come out to be 16 degrees Celsius, and delta To is equal to 30 minus 22 is equal to 8 degrees Celsius. So if we calculate it, that is 16 minus 8 divided by ln 16 by 8, you will get the log mean temperature difference as 11.54 degrees Celsius. Now just rest is just we have to substitute this, that is u0 a delta tm. So u0 how much is given us, uh, yeah, 2100 into 45 into 11.54. So if you calculate it, so it will, you will get this as kilowatts. If I'm writing it kilowatts, so this is the heat transfer in the condenser. I hope this question was clear because we have done a lot of similar type of questions in the previous class. So the answer is A. Okay. So let's move on to the next question. That is question one. We have to determine the mass flow rate of the cooling water and steam. Also simple. Well, we already got what is Q, that is kilowatts. So just Q is equal to M mass flow rate of water Cp delta T of water is equal to, as steam is condensing, it is a latent heat, that is m dot hfg. Okay, so here the trick here is we have to find out hfg of steam, which is condensing at 30 degrees Celsius. Okay, so for that you may need to use the steam tables. Okay. So I hope everybody is aware of how to use steam table. So there is a otherwise you can directly search from the internet also steam properties of steam. Okay, so if you, it's a saturated steam, if you put this, you will get, there are, if there are a lot of softwares also, not software, so you can search on the internet. There are a lot of sites which gives the properties of saturated steam. Otherwise there is a steam table, so you can go through the steam table. So here I'm calculating from the internet. So we can, if we can get the HFG, that is, okay, we will get HF, that is fluid, that is of water, that is 125.745 kilojoule per kilogram, and Hg also, that is dalton of steam. So what is HFG? We know HFG is Hg minus HF. So if you do this, you get the specific is latent heat of vapor and then latent heat as is. So just now it's simple, just equating, that is Q divided by for steam, that is HFG, that is Q is 1090 into 10 raised to 3 divided by 2429.816 into 10 raised to 3. So you will get this answer as you get this answer as 0.44 1.8 kilogram per second. This is the rate at which the steam is condensing. Next, we need to find out what is mass flow rate of water. That is also simple. That is Cp Tco minus Tci, which is 1090 into 10 raised to 3. I'm taking CPS 184180, 22 minus 40. Right. We will get the answer as 32.618 kilogram per second. So this is the mass flow rate of water and mass flow rate of water. So you can corresponding closest answer as C. Okay. I hope this question was also clear. Just the only thing we need to do is we need to find out the HFG of steam at that particular temperature. Next is we will go to the third question, which is related to boiling. So a copper pan has a diameter of 150 mm. The bottom of the pan is estimated to be at 115 degrees Celsius and when placed on an electric cooking range. Estimate the heat flux required to boil the water in this pan. Also determine the critical heat flux. These are the two questions. So we have a pan. So we are supplying heat and this water is there, the pan. So we are supplying heat to the base of the pan and we need to this is at 115 degrees Celsius. Okay. Just a minute, let me check the prop condition of water. Yeah. So the water is at 100 degrees Celsius because we are asked to find out what is the heat required to boil the water. Okay. So as the water is the water is open to atmosphere. This is desaturation of the water. Means as at 1 bar the temperature at which it starts boiling is 100 degrees Celsius. So first we are focusing on nucleate boiling. We are not going to film boiling and also just nucleate boiling. So the famous correlation for nucleate boiling is known as the Roshanow's correlation. So we will use that Roshanow's correlation to find out the heat flux required to heat that is required to boil the water. So the heat flux, the correlation is the heat flux required to at the nucleate boiling regime is mu L HFG G into rho L minus rho V by sigma raised to half CPL delta TE divided by CS HFG times Prandtl number raised to N raised to Q. So this is the Roshanow's correlation. So this is the Roshanow's correlation. Okay. So all these have usual meanings. Yeah, all these have usual meanings like mu L is the viscosity of liquid, HFG is the uh, latent heat of vaporization, and G is gravity. Then rho L is the density of the liquid, rho V is the density of vapor, sigma is the surface tension, CPL. CPL is the specific heat of liquid. Then delta T is the degree of superheat. Then this is CS. CS is a constant that CS is a constant that depends on the surface and solid water interface. So that is usually determined experimentally. And HFG is the specific heat of liquid, sorry, latent heat of vaporization. Then Prandtl number of the liquid, and NCSF. It's usually CSF, CSF, and N. Both are determined experimentally. Okay. Yeah. So next, so this is the first part of a question. So you need to just substitute the values only in this. So what is all the properties are given, that is we just need to substitute 10 raised to minus 6. HFG is given 2257 into 10 raised to 3. Gravity is 9.81. Rho L is 957.9 minus rho V 0.5955 divided by sigma, that is surface tension 58.9. 10 raised to minus 3, so all raised to 1 by 2 into Cp is 4217 into delta T, that is T wall minus T sat. It's given 115 degrees Celsius, so 15 minus 100 is around 15 degrees Celsius. So 15 all divided by CSF. Okay, this CSF is, we will take this as 0.015 and N is equal to 1. So usually most probably this values will be given. Otherwise this value of CSF and N, it is given in both the heat transfer textbook like in Cropera and the UNES sensor for different types of surfaces, and it depends upon the surface and liquid interaction combination. So say for example, for polished surface, this will be different. For rough surface, this will be different. For material also, stainless steel, this will be different. So this will depend on the different surface fluid combination. Like for water combination, for water copper combination, it will be different. Water stainless steel combination, this will be different. Water brass combination, this will be different. So accordingly, we have to select the value of CSF and N. So usually this will be given, but in case it is not given, you can refer to that table. This is given in both the UNES Essential Textbook and in Cropera. So 2257 into 10 raised to 3. Prandtl number is also given, so that is 1.76 raised to 1, the whole cube. So if you do the math, you will get the answer as approximately 4.169 to 10 raised to 5 watts per meter. So this is the heat flux required for nucleate boiling. Okay. Next, we are asked to find out the heat. So for heat is just Q double two into base area of base, like 4.619 into 10 raised to 3 into 5 by 4 into what is the base diameter, 150. So 0.15 whole square. So it will come out to be around 8.16 kilowatts is the heat required to make this boiling. So For critical heat flux also there is a correlation, direct formula you can just substitute, that is Q max is equal to C HFG rho V sigma rho L minus rho V divided by rho V square raised to 1 by 4. So let me just confirm this formula once more. Yeah. So C is a constant and HFG is this specific heat, sorry, the latent heat of vaporization. Rho V is the density of vapor, sigma surface tension, G gravity, then densities raised to 1 by 4. Then for C here, usually we use 0.149 for gives a better increment with experimental data for large horizontal plates. So we will use C is equal to 0.14. So just substitute these values into rho V sigma. Okay, so if you substitute this, you will get the critical heat flux as 1.6 by 1.26 megawatts per minute. So the importance of critical heat flux, it was already discussed in the class, because if you need to design a system or evaporating system, we need to know the critical heat flux, because beyond this critical heat flux, we cannot a further increase in the temperature. As you, if you see the boiling regime, if there is an increase in the uh, delta T, that is the degree of superheat, wall superheat, it will directly go to the film boiling regime, and it will uh, cause the burnout of the heater. So it's very important to understand or calculate the critical heat flux from the design point of view. So let's move on to the next question. So it's a silicon. So it's also related to the boiling case. So a silicon chip has a thickness of 25 mm and has a thermal conductivity of 135 watts per meter Kelvin. The chip is cooled by boiling a saturated fluorocarbon liquid on its surface. The electronic circuits on the bottom of the chip is perfectly insulated. The nucleate boiling constants are given. What are the steady state temperature at the bottom of the chip? So we have a chip here. Okay. So here some we have the we have the coolant, or we can say the saturated fluorocarbon, and this is the bottom surface. This is the T surface, and this is the T bottom. So these are the temperatures. So this is a situation. So the thickness of the chip is 25 mm. So on the bottom of the chip, sorry, so on the top, so it is mounted on somewhere. So say for example on a printed circuit board, and on the top of the chip we are cooling the chip by boiling, or by the phase change heat transfer of a uh, refrigerant, or we can say saturated fluorocarbon. So we need to find out what is the steady state temperature of the bottom of the chip. So we can assume these temperatures are isothermal. So we know if, so for that we need to find out what is the heat flux, that is Q is equal to K of chip times T TB minus TS whole divided by L. So we need to find out for finding out uh, this TB, we need to find out TS, that is the surface temperature of the chip, and also we need to find out the uh, heat flux. Okay. So let's start solving this question. Actually, one of the data is missing, so we need to for finding out TS, we need what is the heat flux that is generated by the uh, Q Q of chip. That is a heat flux that is we need to remove from the chip, that is given as 5 into 10 raised to 4 watts per meter square. This is usually given. This is usually known for a chip. Okay. So let's go back to the this is missing in the question. So you can add this uh, data also. So we know the from Roshanow's correlation, the heat flux required for nuclear boiling is mu L HFG HFG G G is sigma L minus rho L minus rho V divided by S to 1 by 2 into CPL delta T divided by CSF HFG panel on raised to n raised to 3. Sorry. Okay. So this much we know. So what we need to know is delta T. So so I want to rearrange this equation. So after rearranging, you will get T surface minus T sat. That is delta T is equal to TSF HFG Prandtl number raised to n divided by CPL raised to Q surface by mu L HFG whole raised to 1 by 3 sigma divided by G rho L minus rho V raised to 1 by 6. Okay. So this will be our expression. Okay. So so this is our expression. So all the parameters are given, that is CSF and what is CSF is given. If we substitute the values, we will get 0.84400. This all things are given in the question because okay, and 0.01 raised to 1.700 into 5 into 10 raised to 4 440 10 raised to minus 6 into 8 4 1 by 3 8.1 into 10 raised to minus 3 then 9.81 into 161.2 minus 13.4 raised to 1 by 6. So this is our expression. So if you calculate this, you will get this as 15.9 degrees Celsius, that is delta T, that is Ts minus Tsat. So from that we will get T surface is equal to 15.9 plus saturation temperature is given 57, which is 72.9 degrees Celsius. This is the surface temperature of the chip. So we are asked to find out what is the steady state temperature at the bottom of the chip. Now we find out the surface temperature of the chip. So the bottom of the chip, from this expression, we can find out that is Ts plus the heat flux divided by the thermal conductivity of the chip, that is 72.9 plus 5 into 10 raised to 4 divided by thermal conductivity of the chip is given 135. So this will come out to be okay. What is the thickness? You see whether it is 25 mm or 2.5 mm. Mostly it will be 2.5 mm because we cannot see a chip of length, of thickness 2 centimeter, 2.5 centimeter. So it will be 2.5 mm. So if you substitute this, you will get answer as 73.8 degrees Celsius. Okay, so this will be our answer. So let me calculate it once. Answer is right, 73.8 degrees Celsius. Okay, so you can also try this. So answer is A. So the next question is also based on question number 4. So in this question, if the chip heat flux is raised to 90% of the critical heat flux, what is the new steady state value of the chip bottom? For that, we need to find out what is the critical heat flux. Too critical. That is, so this expression I already written in the previous question. So just for critical heat flux, or just substitute the numerical values. So if you calculate this, you will get the critical heat flux as, okay, so 90% of critical heat flux. So Q heat flux 2 is equal to 0.9 times 15.5 into 10 raised to 4. So you will get this as 13.9 into 10 raised to 4 watts per meter square. So the first case, that is the first case, was 5 into 10 raised to 4. So we know the flux, heat flux is proportional to delta TE raised to 1 by 3, right? So Q1 by Q2 should be equal to delta TS by delta TS1 by delta TS2 raised to 1 by 3. Okay, because all the other properties are same. Only varying is the heat flux. So, so this is not raised to 1 by 3, it's 3. Okay. So delta TS2 is equal to delta TS1 into Q1 by Q2, sorry, Q2 by Q1. Yeah, Q2 by Q1 raised to 1 by 3, right? So this is equal to how much? We've already found out this as 15.9. 15.9 into 13.9 divided by 5 raised to 1 by 3. How much it will be? Okay, so raised to 1 by 3. So you will get this as 15.9 into 1.41. So it's 22.4 degrees Celsius. So T surface will become 22.4 plus 57, which is 79.4 degrees Celsius. Okay. So like previous case, so we are asked to find out the base temperature, that is 79.4 plus heat flux into the thickness divided by the thermal conductivity, so it will become 82 degrees Celsius. So the chip temperature at the bottom surface will be 82 degrees Celsius. So this was our fifth question. So next we will go to the uh, sixth question. So this is from the radiation point of radiation part. I hope this question was clear. So it was just application of the Roshanov's correlation. So which is we will be widely using for the uh, boiling, nucleate boiling heat transfer. So it's a next is a uh, radiation question from the radiation topic. So in this spectral distribution of radiation emitted by a diffuse surface may be approximately as shown here. What is the total emissive power and total intensity of radiation emitted in the normal direction and at an angle of 30 degrees from the normal? Okay. So first one we need to catch is the diffuse surface. So for diffuse surface, so the intensity is independent of direction. So it will be, so the intensity of radiation will be same at all directions for a diffuse surface. So this So there is no need of this giving this angle because the intensity will be normal in all the directions. Next one, first we need to find out is the total emissive power. So this is we are given a monochromatic emissivity, so which is dependent on the wavelength. So we need to for finding the total emissive power E total. We need to integrate this over the uh, wavelength. So it is integral 0 to 5 E lambda. So we can divide this into regions 1, 2, 3, and 4, and 5. Okay. So for region 1, we need to integrate over all the regions. For region 1, E lambda, T lambda plus region 2, E lambda, sorry, D lambda plus region 3, E lambda, D lambda plus region 4, E lambda, D lambda plus region 5, E lambda, D lambda. So for region 1, the limits are from 0 to 5. So E lambda is 0. There is no emission from 0 to in an interval of 0 to 5. So it's 0 D lambda plus next range is 5 to 10. So the emission is 100 D lambda. Next is from 10 to 15. Emission is 200 D lambda. Next region is 15 to 20. Emission is 100 D lambda. Plus from 20 to infinity, there is no emission. So the first and second we can cancel. So if we it's a very simple integration. So there is no complex. It's a constant straight line. So it's straight. So it's 10 minus 5 plus 200 into 15 minus 10 plus 100 into 20 minus 50. So you'll get 100 into 5 plus 200 into 5 plus 100 into 5. We will get the answer as 2000 watts per meter square. So this is the total emissive power. Okay. Now we need to find out the intensity. So for diffuse surface, we know intensity E is equal to pi times I. Sorry, the emissive power, total emissive power I is equal to pi times I. So I is equal to E by pi, which is equal to 2000 divided by pi, that pi, which we will get it as 637 watts per meter square. Because this pi is the solid active. Okay, so this is the answer. Next, we will move on to the next question. Consider a large isothermal enclosure that is maintained at a uniform temperature of 2000 Kelvin. What is the wavelength below which 10% of the emission is concentrated? Determine the maximum wavelength at which the emission occurs. So we know, I hope you already watched the lectures. So this is E lambda and this is lambda. So there is for a diffuse surface, sorry, for a real surface, for a black body or okay. So we will get a distribution something like this. Sorry for my bad drawing. So this is the maximum. This is for a particular temperature, right? For a black body. So this E depends upon the emission depends upon the temperature. Sorry, both temperature and the uh, lambda, that is a wavelength. So this is for a particular temperature. So if I am having another temperature, so this will be like we will get a family of curve. Okay, so here, see here in this question, it is saying that the temperature is maintained at 2000 Kelvin. We need to find out the wavelength below which 10% of the emission is concentrated. Yes. So I'm just making only one drawing for only one curve. So this T, this is for temperature 2000 Kelvin. So we need to find out. So we need to find out. This is the total. So this is the total emission. So we need to find out the wavelength below which the what is at the up to what wavelength it is emitting 10% of the 10% of the total emission. This is our question. Okay. So we need to find out up to this lambda one, up to which the 10% of the emission happens. For that, we need to have a black body radiation function. So this is from I have taken from the uh, textbook in Cropera. Okay, so you can find this. So you can find this table from in Cropera. Heat transfer by in Cropera, fundamentals of heat transfer. So this is the function, that is radiation function. So we need to find out up to 10%, right? So up to 0.1 we need to calculate. So if we check, we will get the data for our question is given. That is, this is up to for 10%. That is from 0 to this lambda. This is the function. Okay. So we have lambda t is equal to 2200. I hope how to use this graph or this table is clear. Okay, so we need to find out the up to 10% of the radiation. So from 0 to so up to 10%, we have selected this row. So if it was 25% of the total radiation, then it will be this highlighted one. So if it is 70%, 50%, then somewhere here. If it is 75%, then it will be somewhere here. So according to the question, we can up to we can find out the value of the function. So for our question, it is lambda t is 2200. So it's just simple. We need to find out what is lambda divided by t is also given. So the answer will come out to be around 1.1 micrometer. So from 0 to so what this means is from wavelength range of 0 to 1.1 micrometer range, the body emits 10% of the total radiation. So the 10% of the total radiation is emitted in this wavelength interval. That is what it is. So next first part of question is over. So in the next part, we are asked to find out what is the maximum wavelength at which the emission occurs. So this is the maximum emission. So lambda max we have to find out. So we know lambda t max, which is equal to, we already, this is a standard definition, that is 2898. This is known as the Wien's displacement law. Okay. Wien's displacement law. This is the, it is the, it gives the wavelength at which the maximum emission occurs. Okay. So lambda max we can say as 2898 divided by 2000. The answer will come out to be 1.45 micrometer. Okay. So at this emission or at this wavelength, the maximum emission happens. Okay, the maximum emission happens at this wavelength. That is the interpretation of this result. So this is
This is in the range. It is given up to 10% of the total emission. So we need to use the function. So if you want to find out the maximum wavelength, sorry, maximum, the wavelength at which the maximum emission happens, that is this one, E lambda occurs. Maximum intensity, maximum power radiation occurs is the lambda T is equal to 2898 micrometer Kelvin. So these are some of the basics questions that are related to the radiation part. So here comes the end of our session. So I hope this session was helpful for you and useful for you. So we will see you. We will meet again on the next Monday at the same time. So till then, have a nice week ahead. Thank you. Thanks for joining this.